In this video, we want to take a look at how to find a formula for the general term of a sequence. For our purposes, a sequence is simply an ordered list of numbers. If we want to describe a sequence by writing out the first few terms of the sequence, we can do that just by listing out those terms, a sub 1, a sub 2, a sub 3, and a sub 4. The subscript on the a represents the placement in the sequence. So for example, a sub 4 will be the fourth term in our sequence, and a sub 10 will be the 10th term in our sequence. When given a sequence by listing the first several terms, one goal that we might have for that sequence is to find a formula for the general term a sub n. In other words, we want to find a formula for a sub n in terms of the number n alone, the position in the sequence itself, that will allow us to compute any term of our sequence just by evaluating this formula for the appropriate value of n. Techniques for finding formulas for sequences vary depending on the form of the sequence, but in general, it really is just a form of pattern matching and looking for patterns within the first several terms. In this example, we want to find a formula for the general term a sub n of the sequence whose first 5 terms are 4/5, negative 9/25, 16 125, negative 25 625, and 36 3125. Because we have our first 5 terms of our sequence, we can go ahead and label these A1, A2, A3, A4, and A5 respectively. And we can use this to check our final formula of when n is 1, 2, 3, 4, 5 to make sure that we obtain these 5 values. We probably see some patterns in these terms right away, but any kind of sequence like this can always be broken down into 3 different pieces. The first piece is the sign of the number, whether they are each positive or negative. In this case, A1, A3, and A5 are all positive, and A2 and A4 are negative. And so we have an alternating negative sign here. The first, third, fifth are positive, and the second and fourth are negative. The second part that we can analyze is the numerator of our fraction. And here we're going to look at the numerator ignoring the positive or negative sign. And so our numerators are simply going to be 4, 9, even though it's negative 9, we're breaking the sign and the numerator numerical value apart. Then we have 16, 25, and 36. The last thing to consider, the last piece, is our denominator, which will be 5, 25, 125, 625, and 3,125. By breaking up our sequence like this, we're able to look at our sequence as actually 3 different sequences, find formulas for these 3 sequences separately, and then compose them back together to get a formula for our given sequence. So for our sign, we're going to change our plus or minus signs here to +1 or -1, since we're going to be multiplying by one of those 2 numbers. And so what we notice about +1 and -1 is that both of them are powers of -1. We know raising -1 to an even exponent gives us +1, and raising -1 to an odd exponent will give us -1. And so by looking at these values, one potential formula that will give us the sign is by raising -1 to an appropriate power. And we want it so that when a is 1, we get +1. And so we want to make sure when n is 1, we get an even exponent. One way to do that is to make the exponent n plus 1. And then when n is 1, we get -1 to the second power, which is +1, which agrees with the sign that we have here. And in general, if n is an odd number, then n plus 1 will be even, and so we'll get -1 to an even power, which will be +1. And if n is an even number, then n plus 1 will be odd, so we get -1 to an odd number, which is -1. And this aligns with the 5 signs for our 5 given terms. And so the sign of our terms will be given by the formula -1 to the n plus 1. You could have also used -1 to the n minus 1 here. This will do the same thing. If n is even, n minus 1 will be odd, and if n is odd, n minus 1 will be even. So either of these formulas would work appropriately. For our numerator, we have the numbers 4, 9, 16, 25, 36. By looking at those, hopefully you realize that those are perfect squares. And so we might think that a formula for this would be n squared. But we want, when n is 1, we want to get 4, and 1 squared is not equal to 4. And so in order to get the squares in the way that we want them here, what we need to do is start with our index of n, add 1, and then square that resulting number. So for example, when n is 3, this formula will give us 3 plus 1, which is 4, squared, which is 16, and when n is 3, we do have a numerator of 16. And you can check this on the other 4 terms here to see that this formula will indeed work. And so our numerator is given by n plus 1 squared. Our denominators, 5, 25, 125, 625, and 3,125, are all recognizable as powers of 5. And therefore, we can write a formula for these as just 5 to the n. And here, since we start with 5 to the first power as 5, this is going to just be 5 to the n. We don't need to modify it in any way. Again, we can check this. If n is 3, we get 5 cubed, which is 125, which is indeed what we have here for the third term in the denominator. So we put all of this together, and we see that we get a final formula of our original sequence as -1 to the n plus 1 multiplied by n plus 1 quantity squared all over 5 to the n. And this formula here gives us everything that we need, both for the sign, the numerator, and denominator in the appropriate places. We can always check this. For example, if we pick n to be 5 and substitute n equals 5 in here, we will see that we do indeed get 36 over 3,125. In this example, we want to find a formula for the general term a sub n of the sequence whose first 5 terms are 2, 6, 10, 14, and 18. Again, we want to find some formula for a sub n that when a is 1 through 5, we get the terms listed here. And so what we really need to do is find a way to relate the subscripts 1, 2, 3, 4, and 5 to the numbers 2, 6, 10, 14, and 18. It's possible that you recognize a pattern right away, but if you don't, there's always a way to approach finding a formula for a sequence like this. Notice our sequence is being determined by taking the previous term of our sequence and adding 4. In other words, each term is formed by adding 4 to the previous term. 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 is 14, 4 plus 4 is 18, and so on. And so this might make us think that our sequence is going to somehow be related to the sequence a sub n equals 4 times n. Because each time n increases by 1, the sequence term here would increase by 4. However, we quickly see that this will not work exactly correct. If we use this formula a sub n equals 4n and evaluate this at n equal 1, 2, 3, 4, and 5, we see that our terms would be 4, 8, 12, 16, and 20. And those are not the terms that we have in our actual sequence. However, if we compare our original terms with the terms of our kind of guessed sequence here, the a sub n equals 4 to the n, we notice that if we take the sequence 4 to the n and we subtract 2 from each term, we get the sequence that we want. So this is true all the way across for all 5 of these terms. If we subtract 2 from our blue sequence, we'll get our black sequence. And so that suggests that our formula should actually be a sub n equals 4n adjusted by subtracting 2. And you can easily check that this works for all 5 of our terms of our sequence. And so the general term for our sequence will be a sub n equals 4n minus 2. If you'd like to try a similar example, pause the video and find a formula for the general term a sub n of the sequence whose first 5 terms are negative 3/4, 9/7, negative 27/10, 81/13, and negative 243/16. Resume the video, and a full solution will appear in a few seconds. So we can break this down into the 3 different pieces. The sign is negative, positive, negative, positive, negative. And so we know that will be a negative 1 to a power. And since our first term is going to be negative, we want the exponent to be odd when our index is odd. And so one way to do that would be to write that as negative 1 to the nth power. And that will give us the odd terms being negative and the even terms being positive, which is what we want in our sequence. The numerator values are 3, 9, 27, 81, and 243. And those are all powers of 3. And we start with 3 to the first power, then 3 to the second, and so on. And so we can represent the numerators by the formula 3 to the nth power. For the denominators, we have 4, 7, 10, 13, and 16, and these are all values that increase by 3. So each term in the denominator is 3 more than the denominator of the previous term. And so we can start by thinking of the sequence a sub n equals 3 times n, which are given to be terms 3, 6, 9, 12, and 15. We see that by adding 1 to each of those will give us our initial denominators that we started with. And so our denominators can be found by taking the formula 3n and adjusting it by adding 1 to each. And so our denominator is given by the term 3n plus 1. Putting all of these together, we get a sub n is going to equal negative 1 to the n times 3 to the n all over 3n plus 1. Or if you'd like to simplify the numerator, since both terms are raised to the nth power, we could rewrite it the entire formula as negative 3 quantity to the nth power divided by 3n plus 1.